Hello everyone, welcome to this presentation entitled LED Driver Based on Flyback Converter Dynamic Modeling. So in this video we are going to continue with this series related to the analysis and design of a high power factor of line LED driver based on flyback converter. We have seen in this previous video, Power Electronics number 54, the basic operation and design of this converter. Today we are going to deal with the dynamic modeling of the converter. So in this video we will see first an introduction, then we will talk about the dynamic model, we will show an example, and finally we will do the LT-SPICE verification. Here we have in red the basic converter that we have studied in this previous video, and now we have added in blue the circuitry to operate the converter in closed loop. As we know, this type of applications, LED drivers, need to regulate the current through the LED, so it is going to be kept constant, disregarding the change in the LED itself due to change in the temperature or change in the characteristics of the LED, and also due to changes in the input voltage. So for this we measure the current through the LED using a sensor represented here by H, and then we implement a compensator as shown here. We are using an optocoupler to keep the isolation between the output and the input, and we are using an error amplifier to implement the compensator together with the optocoupler. Here we have to note the reverse polarity. Here we are injecting the reference through the inverting input of the amplifier and sending the feedback signal to the non-inverting input of the amplifier. This is so because here in the optocoupler we have an inversion of the polarity too. So if we increase here the voltage at the output of the error amplifier, then this will increase the current through the LED, and this will increase the current through the collector of the bipolar transistor here, and at the end the voltage here at the output will decrease. So we need to compensate this negative sign here with the change in the polarity here at the input of the error amplifier. So now if the current through the LED increases, the output of the error amplifier is going to increase also, but the output of the optocoupler VC is going to decrease, and this will decrease the value of the duty cycle and ultimately the current through the LED, tending to compensate the initial increase in the current of the LED. Here we have again the schematic of our LED driver operating in closed loop, and we can model our converter using this block diagram here to model the dynamic behavior of the converter. So here we have our converter in which we are injecting the duty cycle signal and generating the output current through the LED. We measure the current with our sensor H. We compare this with a reference corresponding to the current that we want to inject into the LED, send the error signal to the compensator. The output of the compensator goes to the PWM circuit, which has also a gain, and then we generate the duty signal. So what we need right now is to find this block here, this transfer function GD, that relates the dynamic response of the output current with respect to the changes, the dynamic changes of the duty cycle, which is our control signal. And this is basically what we are going to show in this video. As we saw in previous video, we can model our converter from the point of view of the input as a resistance Rg, which is given by this expression here. And from the point of view of the output, we model our converter using a current source that sends the current into the output given by the filter capacitor and the LED load itself. And this is the value of the current that we obtained in the previous video for this current source. For this, we considered that the instantaneous power that goes into the input resistor goes directly to the output. So from this circuit here, we will be able to obtain the dynamic response of our converter. So let's see how to do this in this slide. We are considering the average model. So from the current that is being injected into the output, we will consider only the DC component, which is given by this expression as a function of the different parameters. So now, in order to obtain the small signal model, we take perturbations on this expression here. So we can say that the changes in the output current are given by the different perturbations. We perturb with respect to the duty cycle, with respect to the input voltage, the peak line voltage, and also with respect to the output voltage. We have seen this also in this previous video, Power Electronics number 9, ultra-fast modeling of a PFC stage. So if you are not familiar with this process, please take a look at this video. So from these different partial derivatives, we can get the constants as we are shown here, and these are the final values for the three constants. And here on the left, we have the small signal model of our converter. So this represents the changes on the current that is being injected into the output. We have the output capacitor represented in the Laplace variable domain. We model the LED load using only the dynamic resistance of the LED. Of course, here the ideal diode that we use here is going to be conducting, so this is going to be like a short circuit. And then, of course, because we are in AC signals, the threshold voltage of the model of our LED is a short circuit. So we only have to consider the dynamic resistance of the LED. This is very important because we have to distinguish between the dynamic resistance of the LED and the DC resistance of the LED. The DC resistance of the LED here will be given by the ratio of the DC output voltage divided by the DC current through the LED. And this corresponds to the DC resistance, but this is not the resistance that we have to consider here in the AC model. This would be a mistake, and this would produce a wrong model for our converter. So it's very important to take this into account and use here only the dynamic resistance of the LED. So with this now we have our small signal model for our LED driver. We have substituted here the current source by the three different current sources corresponding to the three perturbations, the duty cycle, the input voltage and the output voltage. And now we are interested in the control transfer function. So it's the duty cycle at the input and the output current at the output. So what we have to do is to make zero the perturbations coming from the input voltage. So for this we get rid of this current source here, and then we have our model to obtain the transfer function GD. We only have to solve this circuit, which is very easy, and we will obtain this expression for the final transfer function. We have a gain KD, which is obtained from this equation, and then we have a zero and a pole that are given by these expressions here. And now let's do an example using the same design that we have seen in previous video, Power Electronics number 54. Remembering a little bit, we have 230 volts at the input, 50 Hz, and at the output we have an LED lamp with an output voltage of 71 volts, output current 0.45 amperes, and output power 32 watts. These are the other parameters that we have seen in the design. So if we use the different parameters that we have here, we can obtain these values corresponding to the dynamic model. The parameter KD, the frequency of the pole, 8.81 Hz, and the frequency of the zero, which is 2.62 kHz. And now we can represent the transfer function of our converter, GD. So we have this expression, as we have seen, at low frequency, the gain of the transfer function is KD. So we have this flat part here corresponding to this gain, which in our particular case has a value of 13.86 dB ohms to the minus 1. And then we have the pole at a very low frequency, because at the end this is a power factor correction converter. The frequency of the pole is 8.81 Hz, and the frequency of the zero is 2.62 kHz. And then we reach another flat region which has a gain given by this expression, and for this particular case is minus 35.6 dB ohms to the minus 1. Now we can check our model by simulation. So here we have the equivalent circuit implemented in LTSpice. This is the current source. We have the output capacitor and then the LED. Here we have a voltage source to generate the value of the duty cycle, and we are superposing here a perturbation with this sinusoidal voltage source in order to measure the dynamic behavior. So here we have the duty cycle, including the perturbations, and then here we have the output corresponding to the current through the LED, including perturbations. And as usual, with these statements here, we can get the perturbations at the input and at the output, and then from them we can obtain the gain magnitude and also the phase of the gain. We have used this many times, so if you are not familiar with this in LTSpice, I recommend you to take a look at this video, LTSpice number 6. This is the first time that we explained how to obtain the open loop frequency response of a DC-DC converter. And here we have the results of this simulation, so we can see that they match very well the theoretical response that we have obtained for our LED driver. This is the gain of the transfer function, and here in this continuous line we have the phase. So here we have the flat part corresponding to low frequency with the gain approximately equal to 14 dBs. Then we have a pole here, and then we have a zero here, and then the other flat part corresponding to approximately minus 35 dBs. So the value of the pole and the zero match very well the values obtained from the theoretical analysis. However, you might say that what we have tested by simulation was not the real converter, was the model that we developed. So it's normal that if both the theoretical analysis is right and the model implemented in LT-SPICE is right, they are going to match very well. In any case, this is good for us to verify that we have done our analysis correctly. The problem is that if we try to obtain the dynamic response, the transfer function of the actual converter, we would require a lot of time for the simulation because we have to simulate the converter with perturbations at very low frequency of only a few hertz, and this will take a lot of simulation time. So the other possibility that we are going to see here to verify our model with the actual converter is to use the step response of the converter. So if this is the transfer function of our converter, we can apply a unit step at the input of our converter, and then we will obtain this unit step response. If we solve the differential equations, then we will get this response that we can see here. And in our case, the frequency of the zero is greater than the frequency of the pole. So if we represent this equation, we will get something like this. We start from a given point, and then the current will increase until reaching the steady state value. And if we use the values in our example, we will see that this initial value is very small, just a few milliamperes. This is the time constant of the response, 18 milliseconds approximately. We know that at the time constant instant we have reached 63% of the final value, so this is 3.1 amperes. In our particular case, and the steady state value is 4.91 amperes. So what we can do now is to take our converter implemented in LT-SPICE and apply this unit step at the input, and with only one simulation we can pretty much verify if the response of our converter is the same as we have predicted theoretically. So here we have the converter implemented in LT-SPICE, as we have seen in previous video. And now what we are doing is to inject a step here superposed to the duty cycle signal. The amplitude of the step here is 0.01, so it's only 1%, not to affect too much to the DC operating point. And we are injecting this step at the time instant equal to 200 milliseconds. And then we are measuring the current here at the output. So this is the current through the LED. And to better see the average value, we are using here a low pass filter with a gain equal to 1 and a cutoff frequency of 10 Hz. So here we are going to have something more similar to the average value of the current. The problem is that when we are adding this filter, we are also affecting the complete dynamic response, because now we will have to consider the dynamic response of the converter together with the dynamic response of the filter. So this is going to affect a little bit. But we are not going to enter into this in detail, so we will see that the dynamic response is pretty much as expected in comparison with the theoretical response. Also, remember that these elements here and here, all these elements that are not available with the distribution of LTSpice are from our Simulink compatible control library. There are videos explaining this library, and also you can download this library from my website. Here we have the results. In blue, we have the signal corresponding to the output current. The current through the LED can be measured here in millivolts, which correspond to milliamperes. And in green, we have the output of the filter. So this is something similar to the average value of the current. At this point here, we have the step, and then we can measure that the time requiring to get in steady state is something like 92 milliseconds. Also, the amplitude here resulting from the step should be 1% of the value corresponding to the unit step response, and this should be something like 49 milliamperes, while we are getting here 52 milliamperes, so it's also quite similar. So with this we can say that we have verified our dynamic model by using a step-up transient simulation in LTSpice. Well, with this we come to the end of this presentation. Please let me know if you have any comment or question. Thank you very much for watching, and I hope to see you in the next video. Goodbye now.